In this episode, we look at two code weaknesses that can create serious security risk even when the rest of an application appears to work normally: hard-coded secrets and unsafe exception handling. These topics matter because attackers often look for information that developers, administrators, or systems accidentally leave behind. A hard-coded secret is a password, application programming interface, API, key, token, encryption key, or other sensitive value written directly into code, scripts, configuration files, mobile apps, or automation. Unsafe exception handling happens when an application responds to errors in a way that reveals too much information or behaves unpredictably. Both weaknesses can help attackers move from guessing to knowing. A leaked secret can unlock access. A detailed error message can reveal file paths, database details, software versions, or internal logic. The main lesson is that secure code must protect not only normal behavior, but also hidden values and failure conditions. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. Hard-coded secrets are dangerous because code is usually copied, shared, backed up, reviewed, deployed, and stored in many places over time. A developer may place a password or key directly in code because it is faster during testing. Later, that code may be pushed to a shared repository, copied into a build process, packaged into an application, or forgotten in an old branch. The secret may then live far beyond the moment when it was convenient. If an attacker finds it, the attacker may not need to break a password or exploit a complex flaw. They may simply use the exposed value. Hard coding also makes rotation harder. Rotation means replacing an old secret with a new one. If a password is buried in many files or applications, changing it may break systems or require a large search. Convenience at the beginning can create long-term risk. Passwords are one of the clearest examples of hard-coded secrets. A program may need to connect to a database, service account, or remote system, and someone may place the password directly inside the code. That may seem harmless if the code is internal, but internal code can still leak. It may be stored in a repository with many users. It may be included in a backup. It may be copied to a developer's laptop. It may be exposed during troubleshooting. It may be accidentally uploaded to a public repository. Once a password is exposed, anyone who finds it may be able to use the same access the application has. The risk grows when the password belongs to a powerful service account. If that account can read large amounts of data or change important systems, one leaked password can become a major incident. The secret inherits the power of the account behind it. API keys create a similar risk, but they are often misunderstood because they may not look like normal passwords. An API key is a value used to identify or authorize a program when it talks to a service. Applications use API keys for cloud services, payment providers, mapping services, messaging platforms, monitoring tools, and many other integrations. If an API key is hard-coded and exposed, an attacker may use it to call the service as if they were the application. Depending on the permissions, that could allow data access, service abuse, fraudulent transactions, excessive usage charges, or changes to configuration. Some API keys are read-only, while others are powerful. That difference matters, but even read-only access can be sensitive if it reveals customer information, internal records, logs, or business data. A key should be treated as a credential, not as harmless technical text. Tokens are another form of secret that can be especially valuable because they may represent an already approved session, application permission, or delegated access. A token might allow a service to call another service without asking for a username and password each time. It might be used in automation, deployment, cloud operations, or application communication. If attackers steal a token, they may be able to act within the limits of that token until it expires or is revoked. Some tokens are short-lived, which reduces risk. Others last much longer or can be refreshed to keep access going. Hard-coding long-lived tokens is especially dangerous because the exposure may remain useful for months or years. Tokens can also be difficult to notice in code because they may look like long random strings. A person reviewing the code may not immediately recognize that the string provides real access to a real service. Encryption keys and other cryptographic secrets deserve special care because they protect confidentiality and trust. An encryption key may be used to protect stored data, secure communication, sign tokens, or verify that information has not been changed. If the key is hard-coded and exposed, the protection may collapse. An attacker who obtains a data encryption key may be able to read information that was supposed to remain private. An attacker who obtains a signing key may be able to create values that appear legitimate. The damage can be wider than one account because a single key may protect many records or validate many actions. Cryptographic secrets should be managed through secure storage and controlled access, not scattered through source code. The security of encrypted data depends heavily on protecting the key. If the key is left in the open, the encryption may become more like a locked box with the key taped to the lid. Hard-coded secrets often spread through source code repositories. A repository is where code and its history are stored so people can collaborate, review changes, and manage versions. The history matters because deleting a secret from the current file may not remove it from earlier versions. If the secret was committed once, it may remain in the repository history unless special cleanup is performed. This is a common trap. Someone notices the mistake, deletes the password from the latest file, and assumes the problem is solved. But anyone with access to the history may still find it. Public repositories make this risk even more serious because automated tools and attackers constantly search for exposed keys, tokens, and passwords. Private repositories also need protection because insiders, compromised accounts, third-party tools, and backup copies can all create exposure. Secrets do not belong in code history. Hard-coded secrets also appear in scripts, configuration files, container images, mobile applications, and build pipelines. A script used for automation may contain a password because it needs to run without a person typing anything. A configuration file may include a database connection string. A container image may accidentally include a file with cloud keys. A mobile app may contain a service token that can be extracted by someone who examines the application package. A build pipeline may print a secret into logs during deployment. These examples show that secrets can leak from many places besides the main application code. Attackers do not care whether the secret came from a source file, a log, a package, or a test script. If the value works, it is useful. Secure development requires thinking about the full path from coding to testing to deployment to monitoring, because secrets can be exposed anywhere along that path. The safer approach is to separate secrets from code and control how applications receive them. In real environments, teams may use secret management systems, environment-specific configuration, managed identities, vaults, secure deployment settings, and access policies. You do not need to configure those tools here, but you should understand the principle. Code should ask for the secret from a protected place at runtime instead of carrying the secret inside itself. Access should be limited so the application receives only what it needs. Secrets should be rotated when exposure is suspected, and powerful secrets should not last forever without review. Logging and error messages should avoid printing secrets accidentally. Developers and security teams may also use scanning tools to detect secrets before code is shared or deployed. The best habit is to treat secrets as live access, not as harmless strings. If it can unlock something, it needs protection. Unsafe exception handling is a different code weakness, but it also gives attackers information or control they should not have. An exception is an unexpected condition that interrupts normal application flow. A file might be missing, a database may be unavailable, input may be in the wrong format, a service may time out, or a user may try something the application did not expect. Applications need to handle these situations gracefully. Unsafe exception handling happens when errors are ignored, handled inconsistently, or shown to users with too much detail. A safe application should tell the user what they need to know without revealing internal structure. For example, a user may need to know that a request failed. They usually do not need to see the database name, server path, code line, stack trace, query text, or internal service address. Those details may help attackers plan their next move. Detailed error messages can leak valuable reconnaissance information. Reconnaissance means gathering information before or during an attack. An attacker may intentionally send unusual input to see how the application fails. If the error message reveals the database type, framework, file path, software version, or internal naming pattern, the attacker learns more about the target. A message that shows a full stack trace may reveal function names, library versions, directory structures, and logic flow. A database error may reveal table names or query patterns. A file error may reveal where files are stored on the server. An authentication error may reveal whether a username exists. Each detail may seem small, but attackers combine small details into a clearer map. Unsafe exception handling can turn the application into a teacher for the attacker, explaining how it is built and where it may be weak. Error handling can also create security problems when the application fails open instead of failing closed. Failing closed means that when something goes wrong, the system moves to a safer state and denies access or stops the risky action. Failing open means the system allows access or continues in an unsafe way because a check failed. Imagine an application that tries to verify whether a user is authorized to access a record. If the authorization service is unavailable, a safe design should not simply allow the request because it cannot check. That would be failing open. Another example is an application that catches an error and skips a validation step, allowing bad input to continue. Attackers may try to trigger errors specifically to see whether security checks break. Good exception handling protects the security decision even when supporting systems, inputs, or dependencies behave unexpectedly. Unsafe exception handling may also hide real problems from defenders. Some code catches every error and does nothing with it, which may prevent useful logging or alerting. The application may appear to continue working while important security events vanish. Other code may log too much, including passwords, tokens, session identifiers, personal data, or full request contents. Both extremes are risky. No logging makes investigation harder. Excessive logging can create a new data exposure. Secure error handling needs balance. The application should record enough information for authorized teams to troubleshoot and investigate, while keeping sensitive details out of places where they do not belong. Logs should be protected because they can contain clues about users, systems, and attacks. Error handling is not only about what the user sees. It is also about what the organization records, protects, and reviews after something goes wrong. Hard-coded secrets and unsafe exception handling can also interact. An application might fail while connecting to a service and then print the connection string in an error message. That connection string might include a username, password, token, or server address. A developer may add detailed error output during testing and forget to remove it before production. A deployment script may fail and display a secret in a build log. A user-facing error page may show internal configuration values because the application was left in a debug mode. Debug mode is a setting that provides extra details for troubleshooting, and it should not expose sensitive information to ordinary users or the public. These combinations are dangerous because one weakness reveals another. The hard-coded secret provides access, and the unsafe error message tells the attacker where to find or use it. As you continue with Security Plus version 8 and SY0801, remember that code weaknesses do not always look like dramatic hacking scenes. Sometimes the weakness is a password left in a file, a token copied into a script, an API key committed to a repository, or an encryption key stored beside the data it protects. Sometimes the weakness is an error message that tells the attacker too much, or exception handling that fails open when it should fail closed. Hard-coded secrets create risk because they turn code into a storage place for access. Unsafe exception handling creates risk because failure conditions can reveal information or weaken control. The secure mindset is to protect secrets separately, limit their power, rotate them when needed, handle errors carefully, and show users only what they need to know. Good code should work safely when everything goes right, and it should fail safely when something goes wrong.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.